Have you ever tried to listen to your favorite radio station, only to find it garbled or replaced by a different station? Well, if so, you might have been the victim of something known as a sporadic E layer. There are concentrations of electrically charged gas called plasma in a region of space known as the ionosphere. They act kind of like mirrors in the sky and bounce radio transmissions over the horizon and interfere with your radio, kind of like two people trying to talk over each other. Even though we've known about these layers for over 80 years now, we still don't fully understand them because they occur at an altitude that is really difficult to explore. The air there is so thin that we can't fly an aircraft, but it's just thick enough that if we were to try to orbit a satellite, it would burn up in the atmosphere. So we've only ever been able to explore a handful. Well, one planet where the atmosphere is much thinner is the planet Mars. And one satellite that is currently exploring Mars is the MAVEN orbiter. One of the instruments on MAVEN is called STATIC. It's designed to measure plasma escaping from the ionosphere, this upper atmospheric layer of Mars. And in the data, scientists were seeing that when MAVEN would fly through a certain region of the atmosphere, poof, there was this big density enhancement of this plasma concentration. Scientists realized that they discovered the Martian equivalent of these layers. It's exciting because now we have a place that we can go to directly explore these layers with a satellite. MAVEN has encountered more of these layers at Mars than we've ever been able to explore here at Earth. At Earth, the layers are temporary and unpredictable, but at Mars they seem to be almost permanent and long-lived at predictable locations. Also, scientists found something that they didn't even know could exist. MAVEN discovered the opposite of a layer. They're calling it a rift, and it's where the sky has been pulled apart, and rather than a concentration of this plasma, there's a depletion. Many models said this actually couldn't happen, but yet they do exist, and we find them at Mars. This demonstrates how little we actually know, and how much there still is to discover. These layers are so common, they happen over our heads all the time. You yourself have probably detected one of these with your own radio, even if you weren't aware of it. And who would have thought that one of the best ways to explore them would be to send a spacecraft 300 million miles to the Red Planet?
Lightning across the solar system. Presented by Science at NASA. Lightning is as beautiful as it is powerful. A violent, hotter than the surface of the sun electrical marvel. But might lightning on other planets be even more astonishing? Consider this. When Voyager 1 flew by Jupiter in 1979, its imager captured areas nearly as big as the U.S., lit up by lightning in Jupiter's clouds. Voyager also captured other, less flashy signs of lightning. University of Iowa physicist Don Gurnett is one of the scientists whose Voyager instrument detected radio waves called whistlers, signs of lightning. New Horizons cameras captured lightning flashes on Jupiter 10 times as powerful as anything ever recorded on Earth. And recently, Juno, flying closer to Jupiter than any previous mission, found that most of Jupiter's lightning is around the planet's higher latitudes, unlike Earth, where lightning strikes primarily over land and most intensely at the equator. Juno detected peak rates of 4 strikes per second, similar to rates on Earth. On Earth, lightning forms because colliding ice crystals and water drops inside clouds create positive and negative electric charges, which become separated by convective forces. When the charges become separated enough, a lightning bolt discharges. Something similar happens on Jupiter. Gases, including water vapor, rise from deep within the planet. As they freeze, ice particles become separated from the water drops by convection, building a charge, which is discharged as lightning. Lightning has also been observed on gas giant Saturn. In 1980 to 1981, Voyager detected radio signals called spherics, which, like whistlers, are signs of lightning. Gurnett says, on Earth, you can hear these high-frequency radio emissions on your car's AM radio as radio static during a nearby lightning storm. Cassini recorded similar emissions at Saturn, revealing that for strong storms, lightning occurred as many as 10 times per second. Gurnett has been involved in the search for lightning on other planets across the solar system as well. Venus, for example, has a hot, dry atmosphere made up mostly of carbon dioxide, suffused with sulfuric acid. Could this brew become electrically charged and generate lightning? When Cassini flew by Venus twice, in 1998 and 1999, Gurnet did a search for lightning with a radio instrument perfect for detecting signs of lightning spherics. However, the instrument picked up no signs at all. That same instrument easily detected spherics during a similar flyby of Earth 2 months later, leading him to believe that there is no Earth-like lightning present on Venus. The European Space Agency's Venus Express orbiter has picked up bursts of electromagnetic waves some scientists attribute to whistlers, but others argue that the instrument's frequency range was too low to detect the usual forms of whistlers. Gurnet has used Mars Express's radar system receiver to conduct a 5-year search for lightning associated with dust storms on Mars. That search didn't find lightning. However, images from the Mars Global Surveyor show bright flashes in dust storms, as well as craters on Mars that some scientists believe to be evidence of lightning strikes on the planet's surface. Stay tuned as this electric story unfolds on science.nasa.gov.
MAVEN is a spacecraft that's orbiting Mars. It's been there since 2014. MAVEN, in this case, is an acronym. It stands for Mars, Atmosphere, and Volatile Evolution. And this gives a clue as to what MAVEN's real goal is. It's to study the top of the atmosphere and how the gases in the top of the atmosphere might escape from Mars away to space.
So the atmosphere of Mars must have been a lot thicker about 4 billion years ago, and today it's very cold and dry. And MAVEN is meant to understand the atmosphere as it is today and how it has evolved into this current cold, dry state.
One of the things we're trying to understand with MAVEN is whether a magnetic field for a planet is important for regulating the climate or allowing the planet to keep an atmosphere. Earth has a global dynamo magnetic field. Mars does not, but Mars has an induced magnetosphere. It has an induced magnetic field.
The upper atmosphere of Mars is being ionized by solar radiation. And so the electrons are being stripped from the atoms in the atmosphere. When that happens, it turns into what we call a state of plasma. This plasma in the upper atmosphere is very conductive. It leads electric currents to flow through it. Electric currents, they shape the magnetic fields that are around them. And that's actually how we see them with MAVEN. We take magnetic field data and we map it around the planet, and from that, the currents emerge. We've known how the currents flow in the Earth's magnetosphere for decades, but we don't know how that works around Mars. We don't know how it influences the interaction with the solar wind, because it determines how energy is flowing into the atmosphere how it's transferred from the solar wind into the system. And that's what we're trying to do with MAVEN. When you just look at the data as it comes down, you're just seeing a little squiggly line, essentially. You're seeing the magnetic field strength and its direction vary as the spacecraft is flying through different regions. And so what you have to do is you have to actually map it to the planet and to this interaction with the solar wind. And then it starts to emerge that you have a drape situation where the magnetic field of the solar wind encounters the planet and it starts to wrap around it. And the reason it wraps around the planet is those electric currents that we are seeing.
The magnetic field in the solar wind is straight lines. You can think of straight spaghetti noodles, and it's flowing towards the planet, and those spaghetti noodles wrap around this basketball-shaped planet. And that's indeed what we saw in the data, the magnetic field lines draping around Mars as a planet. One thing that wasn't so expected was the specific configuration of the electric currents that we derive from the magnetic field data. If Mars is a ball here, it's sort of this cup shape on the day side that loops back on itself, maybe something that looks like this. What wasn't so intuitive to me was the directions of those currents and the fact that it wraps continuously around to the night side, and it makes this marvelously complex current system on the night side as well.
This is the first time that we've been able to actually map out the currents, so we can see where the energy is being transferred, we can see what actually forms the underlying mechanisms creating these induced magnetospheres that are not just common here in the solar system, they're 50% of the planets that have them, of the terrestrial planets. And if you want to understand how the atmosphere of Mars and Venus, why they're so different from the Earth, and why they're so different from each other despite both being non-magnetized, we need to understand their induced magnetospheres first.
So knowing how these global current systems are configured teaches us about how charged particles near the planet are going to move, both charged particles in the solar wind and charged particles from the atmosphere itself that are in the process of escaping to space. So now we can understand better where those particles came from, how they move near Mars, and where they're going to go next. That in turn teaches us about atmospheric escape from the planet and the history of the atmosphere over time. How thick has it been? How much has been removed?